Hi. So yeah, this is exploration of Sylow's theorem part 10. Call this exploration of Sylow's theorem 10. So we're still pretty much obsessed now with the idea that, look, suppose we have a group and we know that the order of the group equals to p to the alpha times m, and we have H subgroup of G. We're saying that, is it true that this implies that there must exist a subgroup H of G such that order of H equals to p to the alpha? Right? That's the key question here. We don't know if this is true or not. So far we proved one special case that suppose order of G equals to p times m, then there exists some H subgroup of G such that order of H equals to p, right? So didn't we establish this before? And now let's think about something else, perhaps another special case. So suppose instead that, and this is what we're working on, what if the power is just 2? Suppose we had that order of G equals to p squared times m. Does this necessarily imply that there exists some subgroup H of G such that order of H equals to p squared, right? So we're trying to establish this, and one way we're trying was by contradiction or a form of contrapositive. Not sure if we pursued that path, but let's first definitively dispose of it, perhaps, and say that it's not gonna, it's unlikely to work for us, and then move on to a different approach. But the idea was, what if we assume that order of G equals p squared times m, but the conclusion is not true? That is, suppose that order of G equals to p squared times m, and at the same time, for all H subgroup of G, it's actually true that order of H does not equal to p squared, right? Can we obtain a contradiction from here? Because if we can obtain a contradiction, doesn't that mean that then our assumption that, doesn't that mean that if order of G equals to p squared times m, it must also be true that there exists some H for which order of H equals to p squared? Right? The key challenge, however, turns out to be trying to figure out, we don't know if it's key, but one of the challenges here turns out to be trying to figure out whether, finding a contradiction here. Just what does it mean to say the order of H is not p squared? And if the order of H is not p squared, and given that we were saying before, we know that the order of H has to divide the order of G by Lagrange, well, doesn't that mean that the order of H must then be of the form p to the t times some L, where L divides m, and t is less than or equal to 2, and at least 0. Well, yeah, so the idea was, okay, sure, what if we know that order of H equals to p to the t times L? So what? Right? And if we recall correctly, this approach didn't seem to be leading us anywhere. And so what we resorted to was just studying what it means, for the order of a group to be of the form p to the 2 times L. That's what we resorted to. So, sorry, p to the 2 times, we're going to use m here. What does it mean for the order of a group to p squared times m, and for the GCD of p and m to equal to 1, right? What do those two statements mean? So And one thing we're noticing is, isn't it true that if, well, this is kind of similar to what we've been doing before, so can't we say that then every subgroup must be of the form order of h times p to the t times l, where l divides m and t is less than or equal to, t is at most 2 and at least 0, okay? So we've explored this a lot. We're not sure if this is going to give us something. It's really important to come up with something new here, something we haven't thought of before. What else would it mean to say that the order of a group is equal to p squared times m? Um, well, I mean, are we guaranteed an element of the form of, are we guaranteed that there is, question, is there some g in G such that order of G equals to p squared times m? Why is this relevant? Suppose we had some G whose order is p squared times m. Would we be saying that the group is cyclic? Sure. If the group is cyclic, so what? Oh, wait a second. If the order of G equals to p squared times m, right, aren't we saying that then if there exists some element little g in G such that order of G equals to p squared times m, aren't we saying that the group G can be generated by the element little g? Okay. Now, if you're unfamiliar with isomorphisms, please look up the idea of an isomorphism. In particular, if G is cyclic, can't we say that phi from G to z mod p squared times m given by phi of G to the I equals to I, right? Can't we say that this is an isomorphism? Phi is an isomorphism. Okay. Okay. If phi is an isomorphism, if this isomorphism phi actually, if this phi that we've defined is actually an isomorphism from G to z mod p squared m, what are we saying? Aren't we saying that if z mod p squared m has an element of order p squared, then G has an element of order p squared? Okay. Does z mod p squared times m have an element of order p squared, is the question. Well, why not? Isn't z mod p squared times m equal to 1, sorry, 0, 1, 2, blah, 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 p squared, and a bunch of other elements, all the way up to p squared m minus 1, okay? So aren't we then guaranteed an element of order p? Yeah, let's see. If we look at z mod p squared times m, are we guaranteed an element of order? Because if we could have an element of order p squared, aren't we done then? Because if we have an element of order p squared, haven't we just found a subgroup of order p squared? But what would it mean for an element to have order p squared? Wouldn't it mean that for that alpha, alpha times alpha gives us the identity? In this case, since we're looking at z mod p squared times m, and we're saying that alpha plus alpha must give us 0, okay? Oh no, what is this? Wait, no, aren't we saying that alpha times alpha times alpha, blah blah blah, alpha multiplied p squared m times is gonna give us, I mean, gonna give us the identity. That's if, and that p squared times m is the smallest power to which when you raise alpha you get the identity. Isn't that what it means to say that order of alpha equals to p squared times m? Okay. Well, in this case we're looking at z mod p squared times m. So we're looking for a number, an element, some number between 0 and p squared m minus 1, such, let's say a number x such that x multiplied by p squared is going to give us the identity. Right? Here, okay, here's a strategy. Suppose that there is always an element, again, we're not sure about this, but, right, so perhaps this will be our potential strategy. Suppose that we found an element, suppose that we're always guaranteed an element in G whose order is p squared times m. Aren't we then saying that G is cyclic? And if G is cyclic, doesn't that mean that G is isomorphic to Z mod p squared m? And if G is isomorphic to Z mod p squared m, aren't we guaranteed then that, isn't it true if two groups are isomorphic, that if one of the groups has an element of a given order, the other group has an element of a given order? So suppose we found an element in Z mod p squared m whose order is p squared. So we found some x in Z mod p squared m such that order of x equals to p squared. Would that mean that there's some element little g in G whose order is also p squared? Okay? If that's true, wouldn't we have then found a subgroup of G that has order p squared as desired? So, but first the question is, before we, here we think about our wet dream come true, right? Best wish come true, that is, that actually Z mod p squared m works. That actually Z mod p squared m has an element of order p squared. If we have this, then perhaps we could find a way to force the fact that there's gotta be an element of order p squared times m. But I know that would be equivalent to saying that every group of order p squared times m is cyclic. We're not even sure if that's a true statement. A lot of confusion, but this sounds too similar to something we've done before, so whether it will work or not is questionable here. So, well, yeah, sure. Is there a number less than p squared such that when you multiply it by p squared you get 1? Right? Well, yeah, sure, right? Isn't, oh shit, well, what's the number? Um, well, I mean, is the number going to be an integer is the question. What does x have to be so that x times p squared equals to 1? Right? Doesn't that mean that x has to equal to, oh, but we're looking at things mod p squared times m. So the question is, well, is x times p squared congruent to 1 mod m for any x? Well, if p and m are relatively prime, doesn't that mean that p has an inverse? Okay, so aren't we saying that x is congruent to p minus 2 mod m? Okay, that's still the inverse. What's the inverse of p squared? Right, is the question. What are we going to multiply by p squared in order to get something that's 1 mod m, that's congruent to the identity? In this case, it's 0. Well, how about m? What's p squared times m? That gives us 0. Isn't that the identity mod m? Okay. Can anything smaller than m be multiplied by p squared to give us the identity? So here's the claim, basically. Here's what we're saying. Can we conclude that the order of m here equals to p squared? Okay. If we can conclude that the order of m equals to p squared, then haven't we just found, since G is isomorphic to Z mod p squared m, can't we say that there is, I mean, if G is isomorphic to Z mod p squared m, can't we say that there's also an element in G whose order is p squared? Okay. If that is true, then aren't we saying that the cyclic subgroup generated by m is going to be, is going to have a counterpart in G? That is, there's going to be some little g in G which generates a subgroup of G that has order p squared. Okay, again, so this seems like it's going to work. Our only issue is, the main question about this is, look, how do we know that there's always going to be an element in the group that has order p squared times m? Otherwise put, how do we know that G is cyclic? Right. how do we know that every group G, or maybe we can put it this way. We've just proved a special case of the special case. Right. Okay, let's first try that. Right. Sometimes it's good to do what we can first. So let's modify the theorem a bit to say something, and let's see if you buy this. Let's say this. Suppose, let's see if you buy this theorem. Okay. Suppose order of G equals to P to the alpha times M. Where's the eraser? Alright. Suppose order of G equals to P to the alpha times M, and G is cyclic. Okay. Suppose we have a cyclic group. Okay, let's write it differently. Suppose G is cyclic and order of G equals to P to the alpha times M. Does that imply that there exists some subgroup H of G such that order of H equals to P to the alpha? Right? Could we prove a special case where the group is cyclic? Right. So let's try that. Suppose G is cyclic. What does that mean? Doesn't that mean that there exists some little g in G such that that G generates the group big G? Little g generates the group big G. Okay? So, in particular, suppose we define the function phi from G to Z mod P to the alpha times M. This is not P squared, it's P to the alpha. Right? So, suppose we define the function phi from G to Z mod P to the alpha times M. Okay, this is alpha again. Given by it gets the element, since little g generates a group G, can we say that every element of the group G is of the form G to the I? Okay, so suppose we define a function that takes G to the I to just I, element of Z mod P to the alpha times M. Can't we conclude then, Z mod P to the alpha times MZ? Jeez. I hope we didn't confuse it the whole time here. Z mod P squared. Okay. Alright, so we're assuming that G is cyclic, and we're saying that, look, that means that there's a generator. Okay. And if there's a generator, can we define this function that takes every G to the I element of G to I in Z mod P to the alpha times MZ? Okay. Here, of course, Z mod P to the alpha times MZ is being considered with respect to addition. Okay. So, claim. What would we need to show? What would we need to prove in order to show that there's a subgroup of order P to the alpha? Okay. In particular, suppose we found some element of G. Suppose we found some X element of G such that order of X equals to P to the alpha. Right? Wouldn't that be enough to show that there is a subgroup H of G whose order is P to the alpha? Namely, the subgroup generated by the element X in G. Okay. Now notice, if this phi is an isomorphism, right? So again, please check that this is an isomorphism. If phi from G to Z mod P to the alpha times MZ is an isomorphism, okay, doesn't that mean that if we can find an element of order P to the alpha in Z mod P to the alpha times MZ, then we also have an element of order P to the alpha in G, right? That is, if we have an element of a given order, if two groups are isomorphic and we have an element of a given order in one, we also must have an element of the same order in another, right? Again, please do verify that. So if you buy that idea, then here's what we're saying. We're saying that, look, we've just found a homomorphism phi from Z mod, we found a homomorphism phi from G to Z mod P to the alpha times mz. Okay? And in particular, if we look at the element m, right, so we just run out of time. We'll just continue from this exact spot and see if we can't find ourselves another special case, right? And hopefully the more special cases we prove, the deeper understanding, and hopefully soon we'll be able to decide for ourselves whether or not this theorem is true. Alright, so yeah, see you in the next video.